So we were doing colored compounds. We had started colored compounds. Previously, we had talked about ligand exchange. We have talked about complexes and their colored complexes, ligands coming in with the lone pairs and they're getting attracted to the copper 2 plus. And we had talked about some ligand exchange reaction that if you add NaOH to a copper sulfate aqueous solution, then the copper ligands which are bonded natively to water molecules, उनकी जगह OH ions आ जाएंगे, and OH ions are going to displace and a pale blue precipitate would form. Here we did one for NH3, that if you have NH3 and water molecules they come in, if you add NH3 a few drops, they react with water to produce OH ions. So you get a displacement with OH, ligands get displaced by OH, you get a pale blue precipitate. And then you have, if you add excess NH3, then NH3 comes in and starts knocking out the OH and water ligands to form this complex, which is deep blue in color. So we did all sorts of ligand exchange reaction, and we had to start with colored compounds. And now the issue is, why are transition metals colored in the first place? So colored compounds is, when we talk about colored compounds, I wanted to make a few points first. And one of the points was that I drew a sodium atom. And I said that sodium has electrons, 11 electrons to be precise. And this is the ground state electronic configuration of sodium. It has 2 electrons in the first shell, 8 in the second, and 1 in the last. Now, this ground state is the lowest energy state. And then I told you that there are all sorts of electromagnetic radiations that are colliding with the atom. And these radiations, they carry energy. And this is going to make the electrons energetic. So these electrons can go into excited state. So this electron over here can jump and move to a higher energy shell or subshell. So it could jump and transition to a high energy state. And that's called an excited state. Now, this is known as an excited state, that your electron from the lower energy levels it gains energy and and jumps to higher energy. So it jumps to high energy shells, and by absorbing frequencies from the spectrum, from the electromagnetic spectrum. So by absorbing frequencies from electromagnetic spectrum. Now the thing is that you have all sorts of frequencies coming in. There's radio waves, there's gamma rays, there's ultraviolet, there's infrared. All sorts of frequencies are coming in, and these electrons might gain energy from any of those frequencies. Now, one thing that I wanted to tell first was that energy levels are quantized. At the quantum level, energy levels are very specified, are quantized. What that actually means is that an electron cannot really exist at any energy level that it likes. For example, why do electrons go further away from the nucleus? Because if they're energetic, then that means that they can overcome the force of attraction that's keeping them close to the nucleus. So these electrons would jump and move further away because they're more energetic and they can overcome the force of attraction that's keeping them close to the nucleus. So this electron is over here. Now, if it gains energy, the thing that's going to happen is that it's not going to gain any energy. It's always going to gain a very specific amount of energy. They're very quantized in very specific levels. It's either going to exist over here, or it's going to gain a very specific amount of energy and move to a higher energy subshell. So these energy gaps are very, very specific. Like, for example, all your subshells and orbitals, they have some very specific energy levels, and they're very rigidly specified. So if you look at 1s, 2s, 2p, and 3s and 3p and 3d, and so on, these are all energy levels. These are all regions in space, and the electron can exist in any one of them. But all these regions, they have very specific energies. So if an electron is residing over here and it jumps to a high energy subshell, and let's hypothetically assume that it needs 100 joules of energy, then that is the exact amount of energy that the electron would gain. It's not going to happen that this electron decides to gain a little less energy and decides to occupy this region, somewhere in the middle. The regions and the energy levels are very, very specific, and the electron would exist in those very specific energy levels. So the energy levels are quantized. That's one very important point. The other thing about this is that energy is proportional to frequency. And there's you're going to learn this in physics as well, that all energies, they're proportional to frequency. what that means is that if the energy levels are very highly specified, they're very specific energy levels, then the electron would only, because energy is proportional to frequency, the electron is going to absorb only very specific frequencies. One real world example for this is that you can think of a swing. Okay, so if you think of a swing, and the swing moves to and fro, right? It moves to and fro like a normal swing. So there's a to and fro motion, and if there's a person sitting on it, now for that person to move, there must be someone over here that pushes that person. So there's this person that's pushing and giving the swing energy. Now this person over here, he pushes the swing and the swing starts to move to and fro. It absorbs energy. Now imagine this is the electron. Now energy always is transmitted in the form of waves. Waves is basically to and fro motion. Okay, particles in a wave are always cyclically vibrating, and that's the form of energy. That's the form energy takes when it travels through a medium. So you have this person pushing the swing. Now this person has to operate at a specific frequency. Why? Because he has to operate the swing at a specific frequency. The swing is not going to gain energy if this person changes his frequency. Okay, he has to push the swing at a very specific time interval. Like if the person is over here, he pushes him, he goes over there and he comes back and he pushes him again. So this person has to push or transmit energy at a very, very specific frequency. So he would be restricted. His frequency would be restricted at which he operates. He can't just randomly start pushing it. The swing will not move if he starts pushing randomly. If he's on the wrong frequency, the swing is not going to move. It's not going to absorb energy. So the person has to operate at a very specific frequency. Galat frequency, if it's the wrong frequency, no matter how big the person is, and no matter how strongly he pushes it, the swing will not move if the frequency is wrong. Okay? For example, if the person is coming back over here and he decides to push him at that point, the swing will not absorb energy. And the other thing, so that's the point. The electron behaves like this. It only operates at very, very specific frequencies. Otherwise, it's not going to absorb energies. And the other thing is, the other thing about electrons is, the other thing is energy is proportional to frequency. What that means is, imagine if this person is operating at a high frequency, that means he's spending a lot of energy. He's pushing the swing a lot. If this person is operating, or the swing operates at a very low frequency, then this person is not spending a lot of energy on it. And wo jo cyclic motion hoga of a wave, to and fro motion, that's going to be lesser. So higher amount of energy needed, more frequency. Lower amount of energy needed, less frequency. So these are few of the points. And there's one extra point, and that is that you're going to see complementary colors. So if you have an atom over here, and this particular atom, whatever the atom is, all sorts of waves are coming in, and they are hitting or colliding with this atom. And the electrons in the atom, the electrons are absorbing energy. So all sorts of waves. For example, there's ultraviolet, there's microwaves, there's infrared, there's visible spectrum. Let's say there's red light, and there's blue frequency. All these frequencies are coming in and they're hitting the atom. And the atom decides to, the electron, remember the electron is going to absorb a very specific frequency and it's going to gain a very specific amount of energy. So if the electron in the atom decides to gain the red frequency, and it absorbs that, so the atom is absorbing red frequency, then all the rest of the waves are going to get reflected back. So which ones are going to get reflected back? There's going to be ultraviolet, there's going to be infrared, there's going to be blue light. All these waves are going to be reflected back except for the red light. And if there's any observer over here, he's going to see all the frequencies except for the one that the substance is absorbing. So what you see are always complementary colors. So when you see a substance, when you see any substance, what that means is, if you look at copper sulfate and it appears blue in color, that means blue is the only, or the frequencies in the blue range, they're the only ones that it's not absorbing. And it's absorbing the other ones, red, yellow, orange, etc. They're being absorbed because you're not able to see them. So you always see the opposite. Then another thing about this is that there's this thing, the absorption of frequencies going into excited state. All atoms have electrons. Transition metals are not special atoms. All elements have electrons, and the electrons go into excited state by absorbing different frequencies. So there's nothing special about it. Transition metals, the same thing would pretty much happen. Their electrons would also absorb energies. The only difference between a transition metal and a normal metal or any other compound is that transition metals tend to absorb frequencies from the visible spectrum, which is why they appear colored to us. So there's nothing special about transition metals. They behave in exactly the same way as other atoms do, except for the fact that they absorb frequencies from the visible spectrum. If you have sodium, so NaCl appears white in color. So maybe it's not absorbing frequencies from the visible spectrum. It might be absorbing frequencies from the ultraviolet range. Or if there's any other compound that appears white, they might be absorbing frequencies from some other region which you can't see. So अगर आपकी जो the frequencies that you're getting, if I mean, for example, look at this atom. If it had absorbed, instead of red, it had absorbed ultraviolet, what would you observe? I mean, you wouldn't feel a difference because ultraviolet तो पहले ही नजर नहीं आ रही थी. तो जब reflect होगी and ultraviolet is missing, you're still not able to see it. So what's the point? I mean, there wouldn't be any observable difference because you can't see ultraviolet in the first place. So any other frequency that's absorbed, you don't even see them. You can't even notice them. Like frequencies from the visible spectrum, if they are absorbed, then you can obviously observe a difference. So transition metals, they tend to absorb frequencies from the visible spectrum. The next thing is, I mean, why do they absorb frequencies from the visible spectrum? I mean, what's the difference between a sodium's electronic configuration? Because all atoms, they have pretty much the same electronic configurations. So if you look at sodium plus 1's electronic configuration, it's 1s2, 2s2. It's the same electronic configuration, 2p6. And the 3s is empty, and the 3p is empty as well, and the 3d is empty. So no difference at all. I mean, it's all atoms have the same electronic configuration. Now, in the case, I mean, I'm going to cut these out. Now, the difference in a transition metal is, for example, if you have Fe2 plus, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. Now the difference comes in this d subshell. Transition metals have this d subshell. Remember, all transition metals, the last electron in a d block element, the last electron goes into a d subshell. So this visible spectrum, the electrons that are jumping around in the d subshell, they actually absorb energies in the visible range, and they actually absorb frequencies in the visible spectrum. That's the only difference that they have compared to other metals. And there's something going on over here as well with the d subshell. Something happens to the d subshell which makes or changes its absorption frequency. So what actually happens to the d subshell is, for that I would need to actually bring in a d subshell, and we're going to study a d subshell first, and then we're going to talk about it. But I'll just give you an idea. For example, you have copper sulfate, anhydrous, without water. Now, without water, copper sulfate anhydrous is white in color. It absolutely has no color, which means that if it's appearing white, it means it doesn't absorb any frequency from the visible spectrum. But as soon as you add water to it, it ends up forming Cu2 plus aqueous and SO4 2 minus aqueous. And I previously told you that your Cu2 plus aqueous is basically your copper complex with water molecules, 6 of them, having a total charge of 2 plus. Now, this complex over here is blue in color. Now, initially, without the ligands, copper did not have any color at all. And with the ligands, all of a sudden, copper is now showing blue color. So what happens when ligands approach a metal line, especially a transition metal line? So I'm going to quickly draw a diagram first. And the axis, this would be the z-axis. Okay, so these are the 3 axes. Now, initially, this is white in color. Without the ligands, it's white in color. So this copper ion just roaming around without any ligands. It appears white. It doesn't absorb any frequency from the visible spectrum. But as soon as the ligands come in, you have these water molecules coming in with the lone pairs, and they're getting attracted to the copper 2 plus. Now, when they approach, something happens to the copper and its electronic configuration that it starts absorbing frequencies from the visible spectrum. Okay, so here are all the water molecules coming in. Remember what the electronic configuration of copper was. Okay, if I remove the ligands, it's going to appear white in color. As soon as I place the ligands around it, it starts appearing blue in color. So I'm going to look at the electronic configuration of copper as well. Copper is 2+, which means it's argon. This is up to 3p6. Then there's 3d9 and 4s0. Now, copper's inner shells are all full. Up to the third shell, almost all orbitals are full. So I'm going to draw an inner shell as well. Okay, let's say this over here is the inner shell. Okay, these are electrons inside the third shell. Now, copper's outer shell is completely empty. The 4s, like any metal, the atom, when it forms an ion, it loses electrons from the outermost shell, which in this case is 4s. So the 4s, 4p, the outer shell, the fourth shell is completely empty. So let's mark that one as well. So this over here is the outer fourth shell. Okay, that's the outer fourth shell. Now, the inner shell, this green one over here, remember, is completely full with electrons. Okay, this part up till 3d9. The third shell, 1s2, 2s2, 2p6, 3d up till 3d9, they're all completely full with electrons. I mean, there's one electron missing, but otherwise this area is completely occupied by electrons. So all of it is full. So this is what copper does. Attracts the water molecules. All the water molecules, they come sticking to it because this thing has positive charge. And I'm now going to talk about that when these ligands, they approach. Okay, for example, this ligand was roaming around. And when this ligand approaches and forms a dative bond. Now, this is an octahedral complex, which means all the ligands are approaching on the axis. On the different axes, all the ligands are approaching. Now, I'm going to bring in the d subshell. So here's the d subshell. If you look at the d subshell very carefully, then you would notice that, and we've studied the d subshell earlier as well. If you look at the d subshell has 4 lobes. The 5 d orbitals. One is dyz, the other one is dxc, then you have dxy, dx square minus y square, and then there is dz square as well. Now, all your d subshells, they have 4 lobes. The electron can exist in these 4 lobes. Now, the first 4 are exactly identical. The electron would exist, they're exactly identical. The only difference is that the orientation is different. This is px, py, pz. The only difference was that the orientation was different. The same is pretty much the case over here as well, that the orientation of the d subshell is actually different. Here it's lying in the yz plane. Over here it's lying in the xy plane. Over here it's in the over here it's in the xc plane. Over here it's in the xy plane, and over here it's lying on the axis. Okay, every time it's a different space. Okay, now the thing is, these the first 3 d orbitals, if you look at the electron, then the electron is lying between the axes. Like you have the z-axis and the y-axis, and the electron exists between those axes. You have the z-axis and the x-axis, the electron is existing between the z and x-axis. Over here, the electron is existing between the x and y-axis. So these 3 orbitals, they lie between the axes. So I'm going to sketch them on this. Remember, this was my third shell. Now 3 of the orbitals, they lie between the axes. So I'm going to sketch them in pink. So they would be occupying regions between these axes. So I'm just going to sketch, although it's a 3-dimensional diagram, I'm just going to make it rough. Okay, so a rough sketch, they're places between the axes, and these electrons, they exist between the axes. Okay, not on the axis. So I've drawn them together. I mean, all the places between the axes would be occupied. So what about the other d orbitals? If you look at the other d orbitals, this one is on the x and y axis, the electron would exist on the x and y axis, and over here the electron would exist on the z axis. So I'm going to draw them in green. Okay, I'm just going to make a rough sketch on. So the last 2, the electron would be existing on the axis. Okay, so all these electrons, they are going to exist on the axis. Collectively, this is a d subshell. Take a rough sketch of a d subshell. If you put all of them together, this would be the rough sketch of a d subshell. So these are all the places where 10 electrons would exist. Okay, so I'm not talking about them individually. Each orbital, I've drawn them collectively, and I'm also going to write that these 2, they lie on the axis. So these two, they lie on the axis. Now, based on this, if you look at copper had 9 electrons in the d subshell. So the d subshell is almost completely full. I mean, there's 1 electron missing, but apart from that, that 1 electron, it's almost full. So the 3D is completely full. Now the issue is what happens and why do they become colored when this ligand over here approaches. So this molecule, water molecule, would get attracted to the copper, even though this molecule has nothing to do with the inner d subshell. वो तो बाहर जाके park हुआ है ना. It's sitting outside in the 4th empty shell, because there is no space over here. So these lone pairs can't come over here in these spaces. So the water molecule is sitting outside the 3rd shell. But one thing that would happen is that since the lone pair is coming in the direction of it's lying on the axis, the problem would be that it's going to exert a force of repulsion. I mean, even if the water molecule has nothing to do with the inner d subshell, the water molecule and its lone pairs are lying very close to this green orbital, the one that we see over here, and it's going to exert a force of repulsion. And the same would happen pretty much with this other one as well. I mean, it's going to approach, and they're going to mutually repel each other. The inner d subshell, all of them would start to repel. And who's getting repelled? The green orbitals. Right? Every time it's the green orbitals that are the ones that are lying on the axis. They are the ones that are facing the repulsion due to the presence of the ligands. If you remove the ligands, then immediately that force of repulsion would vanish. Okay, so if I get rid of this water molecule, then there's obviously no force of repulsion. I bring in this water molecule and it sticks over here, then obviously there's going to be a force of repulsion. Now the issue is, what does that force of repulsion, if you add the ligands, what happens that makes it colored compounds? I mean, why did the presence of water molecule and this tiny force of repulsion make it a colored compound? Now, originally, all these d subshells were identical. Like, if I list all these d subshells, they're called degenerate orbitals. They're exactly identical. So I'm going to list them. Your d orbitals are 3d xy, 3d xz, 3d yz, 3d x square minus y square, and 3d z square. Now, all of them are identical. The only difference is orientation. Like px, py, pz are identical orbitals. The only difference is orientation. So these are called degenerate orbitals. So these are referred to as degenerate orbitals. And what happens, what degenerate means is that they have the same energy level. There's no difference. But in the presence of these ligands, there's going to be a difference. Like if the water molecules come in, the green ones are going to face a lot of repulsion. So it's going to be much easier to keep the electrons in these pink orbitals. The ones that, because they're not facing the lone pairs over here. Okay, the green orbital, it's going to be much more difficult to keep an electron, and it's going to be much easier to keep an electron in the pink orbital over here. So your d subshell is comprised of 2 sets of orbitals. I mean, roughly, if I split them up, there are 3 orbitals which are lying between the axis, and the 2 orbitals lying on the axis. Okay, the green ones over here. The green orbitals are going to, it's going to be very difficult for you to keep electrons in the green orbitals, and relatively, it's going to be easier to keep electrons in the pink orbitals. So your d subshell is going to split in energy levels. The pink ones would be at the lower energy level, easier to keep electrons over there. So it's going to be 3dxy, 3dxz, and 3dyz. So it's going to be easier to keep electrons over there. And the green ones, it's going to be kind of difficult to keep electrons over there. And the electron has to face a lot of repulsion. So it's going to be an energetic electron. Otherwise, it won't exist over there. So these 2 orbitals would be at the higher energy level. So this is known as the splitting of the d subshell. So ligands, so I'm going to write this down. So due to repulsion from lone pairs on ligands, your d subshell splits into 2 energy levels. And it splits into 2 energy levels, and there's going to be an energy gap between the 2. So there's going to be delta E, and there's going to be an energy gap that would be created between the 2 d subshells. So the next thing that we studied was that I told you that by definition, the transition metal ion, the definition is that the d subshell must be incompletely full. So in the case of copper, it has 9 electrons. So there's going to be 2 electrons each. in the lower orbitals and 2 electrons in this upper orbital, and there's going to be 1 electron missing. Now, it's very important that there is some space empty in the d subshell, because what's going to happen is that electrons, there would be all sorts of frequencies that are coming in. So electrons in the lower d subshell might gain energy, and this specific amount of energy, and they might go into excited state, and they might jump to the higher energy d subshell. I mean, what that basically means is that electron can actually switch from the green orbital or the pink orbital. It might gain energy and move to the more energetic region where there's more repulsion. For it, it needs to have more energy, so it can face the repulsion. So electrons can sort of move between or switch between orbitals, but for that they need to gain energy. And this electron over here might jump and might move because there's an empty space over here. So you're now going to have 2 electrons in the upper d orbital. Now, the important thing about this is that this specific energy gap that we're talking about over here, this specific energy gap, delta E, the electron is going to absorb some form of frequency so that it can jump and gain that particular amount of energy. Now, this energy gap matches frequencies from the visible spectrum. I said matches frequencies from the visible spectrum, which is why a frequency from the visible spectrum actually goes missing and you're able to see a complementary color. This subshell splitting does not happen in other elements. They don't even have a d subshell to begin with. अच्छा खाली होना जरूरी है क्योंकि if it was completely full, then where would the electron go? I mean, the electron cannot jump and move to this orbital over here because it's already full. So you need to have some space available so that the electron can jump, and there might be an empty space in the high energy d subshell, and it's going to absorb frequency. So this particular energy difference exactly matches frequencies from the visible spectrum, and because of that, things appear colored to you. And this energy gap keeps changing, which is why different complexes have different colors. Why does it keep changing? Because if you change the ligand, like if I put NH3 instead of water over here, then the amount of repulsion that's going to be faced by these green orbitals over here would be different. And so the energy gap that's going to be created is going to be different as well, which is why a different frequency would be absorbed, and you're going to see a different color if the complex is different, if the ligands are different. So that's the basic idea so far. So writing the description now of the whole process is, the first point would be that why do the d subshells split? Due to repulsion. So due to repulsion from lone pairs on ligands, or we can say ligand lone pairs, due to repulsion from ligand lone pairs, and this only happens when a complex is formed. So when a complex ion is formed, 3D subshell splits into 2 energy levels. Splits into 2 energy levels. And we're going to show the 2 energy levels. So in an octahedral complex, and this is specifically for an octahedral complex. In an octahedral complex, all the ligands, they approach on the axis. So in an octahedral complex, the d subshell, which is originally 3dxy, 3dxz, 3dyz, 3dx square minus y square, and you have your 3dz square. They're going to split into 2 separate energy levels, and you have your 3d x square, the ones on the axis go to a high energy level, and the ones between the axes are present at the lower energy level. Anyways, these would be the 2 sets of orbitals. So the next part would be that an electron from the lower energy 3D subshell or 3D orbital gains energy and moves to the higher energy 3D subshell. So it gains energy and moves to a high energy 3D orbital. And since the next point would be that since energy is proportional to frequency, the energy gap delta E between the 3D orbitals exactly matches, or simply write matches, frequencies from the visible spectrum. And the last part would be hence a complementary color is observed. So complementary color is observed. Okay, that is going to be your 5-point or 4-point explanation. They're going to ask you to draw the splitting pattern of a 3D subshell, and you have to write. It's usually a 4-mark question, and this is all that you have to write. So why does changing ligand changes the color of the complex? So what happens now is the next part is that whenever you change any one of the ligands, like the ligands can get exchanged. So if we go and change any of the ligands, for example, the water over here could be substituted by ammonia, NH3. Now, if it's substituted by NH3, the complex would change color. And the reason is that if you bring in other ligands, then the kind of repulsion that this 3D subshell would face would be different. So, for example, just hypothetically speaking, if the lone pair over here has a very strong negative charge, then that means it would be very hard to put an electron in the green orbital. So the electron over here in the green orbital over here would need a lot of energy. So this energy gap depends on the repulsion of the ligand. So if you have a different ligand, a different energy gap is created. And because of that different energy gap, a different frequency is going to be absorbed, which is why a different complementary color would be seen. So this splitting and the energy gap between the D subshell, it depends a lot on the ligand. If you change the ligand, there would be different repulsions that would be faced by 3D subshell, and the splitting pattern would be different, or the energy gap between the two sets of D orbitals would be different. So I'm going to write down the description now, or the explanation for this in words now. So the thing that you're going to write down is that changing ligands, or we can say the different ligand lone pairs. So different ligand lone pairs, they exert a different amount of repulsion. And because of that, different ligand lone pairs exert a different amount of repulsion. So a different energy gap delta E is created. And since obviously E is proportional to frequency, a different frequency from the visible spectrum is absorbed. From the visible spectrum is absorbed. And that's going to be your explanation, and a different complementary color would be seen. Now, it doesn't change drastically, and a different complementary so a lot of time the complexes are very close to in color, even if you change ligands. For example, in the case of copper with 6 water molecules is blue in color, but you bring in ammonia, it becomes a darker blue. It becomes deep blue. If you bring in OH, it becomes pale blue. Okay, but if you bring in Cl-1, then it becomes yellow. So a lot of times the changes in colors could be very gradual or slight, especially when it comes to OH or water or NH3. The colors are not going to change that drastically. There's going to be some difference, but not that huge a difference. Okay, but hopefully you get the point that changing the ligands would change the color of the complexes. So the question is, why are copper 1+ salts not colored? And for that, we need to look at the electronic configuration of copper 1+. Now, if you write the copper 1+ electronic configuration, you would realize that it's argon, and it was originally copper's electronic configuration was 3d10 and 4s1. Now, because it's 1+, this is gone, so it's 3d10. Now in copper 1 plus, the reason it's not colored is that copper 1 plus, the 3D subshell is completely full. So the iron has a full 3D subshell. Now, because of that, a transition cannot really happen. Like if the 3D is completely full, even if it has split into two sets of different energy levels, if all of them, they have 2 electrons each. A transition, an electron cannot jump from the lower energy to the higher energy because there's no space available. So you need some sort of empty spaces so that the transition could happen. So that's the reason why if the D subshell is completely full, and that is also the case with zinc. Zinc forms iron, but its 3D subshell is also completely full, which is why, and I can add zinc to this. Okay, we can add zinc 2 plus, same reason for that. So we can write the answer: electron cannot move from a lower energy D subshell to higher energy D subshell. As no empty spaces are available. Available in the D orbitals. So no transition is possible. All the D subshells would be full. So the electron cannot gain a frequency because there's no room or space available to put that electron in. Because that question might also come. What we're going to talk about now is that if you have different shapes of complexes, splitting pattern is going to be different. The D subshell splitting pattern so the D subshell. As we were talking about, the D subshell splitting pattern is going to be different. For tetrahedral complexes. Now the thing with the tetrahedral complexes, the entire splitting pattern is going to be different. Now the thing with the tetrahedral complexes, okay, if you go back and have a look at the octahedral complex. Now in an octahedral complex, all the ligands were approaching on the axis. So कौन से orbitals में electron रखना मुश्किल हो गया था? The electrons that were lying on the axis, it was difficult to keep electrons over there. Now complexes can have all sorts of shapes. We're not going to discuss all the shapes. We're just going to discuss octahedral and tetrahedral. Now, if you go and have a look at a tetrahedral complex, which is this one over here, the one that I've opened in front of you. Usually, when you have bigger ligands, you can't fit 6 of them around, so only 4 ligands get attached to copper. Now, the thing with this is that none of the complexes are actually attacking the copper on the axis. Okay, they're all making an angle of 109.5, so none of them are lying on the axis. So in this case, the issue होगा कि axis के ऊपर electron रखना would actually be easier, would kind of be easier, because they're not. Let's say this is the axis, so the lone pair is not really on the axis. Okay, it's kind of at an angle from the axis, so it would be actually easier to keep electrons on the axis, and more difficult to keep electrons between the axis in a tetrahedral complex. So the thing would be exactly the opposite of octahedral complex. So when the splitting happens on the D subshell. Let's go back. Okay, when the splitting happens, now in this case, the whole thing would be opposite now. That on the axis, it would actually be easier to keep electrons. So 3d x square minus y square and 3d z square would be at the lower energy D subshell, and keeping electrons between the axes would actually be kind of hard. So in a tetrahedral complex, always remember that the splitting pattern, the rest of the, why are they colored? The whole explanation would be exactly the same. There would be no difference, except that you have to draw a splitting pattern in which, so you have to draw a splitting pattern in which you have the ones between the axes at the higher energy level. So 3dxy, 3dxz, and 3dyz would be at the higher energy level, and the ones on the axis, 3dx square minus y square and 3dz square, would be at the lower energy levels. And the rest of the explanation would be exactly the same, that there's going to be an energy gap, and that energy gap would match frequencies from the visible spectrum, and electrons would jump from the lower energy to the higher energy, and when they absorb that particular frequency, it's going to be from a visible spectrum, which is why you're going to see a colored compound. So the rest of the explanation would be exactly identical.